that govern the entire physical world around us. So we're looking at kinematics, which is essentially the branch of physics that deals with the study of motion, but without actually worrying about the forces that cause that motion. We're just looking at the pure, beautiful mechanics of how things move from point A to point B.
Okay, let's dive into this. Right now, you might be sitting in a chair feeling completely stationary. But are you truly standing still? The answer, incredibly, depends entirely on who is doing the looking.
So here's our roadmap for this explainer. We'll start with the relativity of motion, categorize the ways things move, figure out scalars and vectors, tackle speed and acceleration, decode some equations of motion, and finally, look at the absolute magic of free fall. Don't worry, we'll start with the absolute basics before we build up to the math.
All right, part 1, the relativity of motion.
In physics, a body is only in a state of motion if it changes its position with respect to its surroundings. Think about being a passenger on a moving train. To the person sitting right next to you, you're completely at rest, right? The distance between you two isn't changing at all. But to an observer standing outside on the platform, that exact same passenger, you, is rocketing by at 60 miles an hour. This means rest and motion are not absolute. They are entirely relative. You literally always have to specify the observer. Moving on to part 2, let's look at exactly how we categorize the way things move.
And this brilliantly illustrates the 3 major categories of motion we see everywhere in the universe. First up, translatory motion. This is when all particles of a body move parallel to each other along a path, like a rolling bowling ball or a car driving down a road. Second, we have rotatory motion, where a body just spins around a fixed point or axis, kind of like the blades of a ceiling fan. Finally, vibratory motion, which is that rhythmic back and forth movement about a central point, like a swinging pendulum or the strings of a guitar vibrating after you pluck them.
Okay, part 3, scalars, vectors, and direction. This is where we learn the vocabulary of movement.
In physics, we divide physical quantities into 2 basic camps. Scalar quantities are completely described by just their magnitude or size. Think of things like temperature, volume, or simply the distance you walked today. Vector quantities, on the other hand, require a magnitude and a direction to be completely described, things like force or velocity. And adding a direction, it absolutely changes the math of how we calculate movement.
Now, what's really interesting about this is how we actually draw this out graphically. Let's say a car is moving 50 kilometers per hour to the east. We use a coordinate system like north, east, west, south. Then you just pick a scale, say 1 centimeter equals 10 kilometers per hour. Finally, you draw a 5 centimeter line pointing straight east, ending in a little arrow. The length tells you the speed, and the arrow gives you the exact direction. It's super simple but incredibly useful.
This naturally brings us to a massive distinction in physics: distance versus displacement. Distance is a scalar. It's the total length of the actual, usually messy path you took to get somewhere. Displacement, though, is a vector. It doesn't care how you got there. It is strictly the shortest, directed straight line from your starting point to your finishing point. Let's look at this visually. Imagine you need to get from point A to point D. If you take the long, winding path up through B, over to C, and then down to D, that entire journey is your total distance. But your displacement? That is simply the straight, direct arrow cutting right across the bottom from A to D. Displacement only cares about where you started and where you finished.
All right, part 4. Let's put this vocabulary into action with speed, velocity, and acceleration. We've all heard of speed, right? It's just the distance covered in a unit of time, but it actually comes in different flavors. Uniform speed is that perfect, constant highway driving, where you cover the exact same distance every single second. Non-uniform or variable speed is city driving. You're speeding up, slowing down. Average speed is just your total trip distance divided by the total time. And instantaneous speed? That is exactly what your speedometer says at one tiny split fraction of a second. But remember those vectors we just talked about? When we take speed and give it a definite direction, like 50 meters per second east, it becomes velocity. And what happens when that velocity changes? If you speed up, slow down, or change direction, that time rate of change is what we call acceleration. Acceleration isn't just about speeding up, though. Sure, if you step on a car's gas pedal, your velocity increases over time. That is positive acceleration, acting in the exact same direction you're moving. But if you suddenly hit the brakes to stop at a red light, your velocity decreases. That is negative acceleration, also known as retardation, and it acts in the complete opposite direction of your motion.
Which brings us to part 5, decoding the equations of motion. These are basically the cheat codes of the universe.
So, the crucial point is that we can actually use simple geometry to predict the future of a moving object. Take a look at this blue line representing an object speeding up from an initial velocity to a final velocity over a period of time. Because acceleration is the change in velocity over time, it is literally just the mathematical slope of this line. By calculating that slope, we get our very first predictive equation. Final velocity equals initial velocity plus acceleration multiplied by time.
Let's see how this builds. If the slope is acceleration, what is the area underneath that line? Amazingly, the total area under a velocity time graph perfectly equals the total distance traveled. Look at the shape under the line. It's just a rectangle and a triangle stacked on top of each other. If we just add the area of that rectangle to the area of the triangle, boom, we derive our second equation of motion, linking distance, initial velocity, time, and acceleration.
And we can take it one step further. Sometimes you just don't know the time variable. Instead of breaking the area into a rectangle and a triangle, we can calculate the area of the entire shape as one single geometric object called a trapezium. When you do that algebra, time cancels out entirely, leaving us with the third equation of motion. It beautifully connects acceleration, distance, and both initial and final velocities without even needing to know the time.
Finally, we arrive at part 6, the absolute magic of freefall.
Freefall is this incredible type of motion where we just completely ignore air resistance, and the only thing acting on an object is the constant pull of Earth's gravity. The famous scientist Galileo discovered that this gravitational acceleration is actually constant for all bodies near the Earth's surface. It pulls everything downward at a super precise rate of about 9.8 meters per second every single second.
Now here is where it kind of breaks your brain a little bit. If you drop a heavy rock and a light sheet of paper right now, the rock obviously hits the floor first. But that is solely because the air in the room is pushing back against the paper. If you were to suck all the air out of a large glass tube and create a vacuum, and drop them both at the same time, that heavy rock and that light paper will hit the bottom at the exact same millisecond. Without air resistance, mass simply doesn't matter. Gravity accelerates them identically.
Think about that for a second. Without air resistance, a giant boulder and a tiny feather would plummet to the Earth in perfect synchronization. The rules of kinematics are constantly working all around us, usually just hidden by friction, air, and our varying perspectives. So as you go about your day today, ask yourself, what other invisible forces are secretly acting on you right now, dictating every move you make? Keep questioning, keep observing, and thank you so much for joining me to explore the beautiful mathematics of motion.